Okay, we continue from the last time. We gave precise definition of limit. So note, this definition can be confusing. So I want to give some examples at the beginning of this lecture about how you can get confused about this definition and remind us what the right definition is. Okay, so first, definition. So this is going to be a wrong definition. Let's see if you can see why. So let fx be defined on AB, but not x0. Then the limit of fx as x goes to x0 equals L if, and remember last time we had something in a box here. So what if we say for all epsilon there exists x such that fx minus L is less than epsilon. Okay, so we're saying for any epsilon, there exists some x so that the value at x is very close to L. So I can make epsilon as small as L. I can get fx as close as I want to L. But this is not right. Okay, so so not correct. So for example, if I defined a function like this, so the function is x for positive numbers and 0, but it's 1 for negative numbers. Then by above definition, limit x goes to 0 of fx equals 1. Because we could take in the above x equals 1. There's always a value of x such that the value of the function is close to 1. In fact, there's always a value of x such that the value of the function equals 1. So the limit there equals 1. But by the correct definition, as we saw last time, the limit as x goes to 0 of fx, so this is fx, of course, does not exist. Okay, and why was that? Because there's a jump in the function. We'll talk more about that. Okay. So here's another definition, which is wrong again, although this one is closer to being right. So we have to be careful. So let's take the same start. And let's say for all epsilon greater than 0, there exists delta greater than 0, such that if x is close to x0, then the value of the function is close to n. Oh, didn't mean that, I meant close by delta. Okay, so this definition is wrong as well, but it's a bit harder to see why. Okay, and the answer is because we missed out greater than 0 here. Okay. So if we take that definition, what do we get? If I take fx equals x squared for all x not equal to 2, but I let it be a different number, say 1 at 2. So remember from last time that the limit does not depend on the value of the function where the limit happens. But if I use this definition, then it does depend. So by above definition, the limit as x goes to 2 of fx actually does not exist. But by correct definition, the limits of fx as x goes to 2 exists and it equals 4. So remember, if we draw the graph, so the graph looks something like this. So it's the x squared graph, except at this point, where the value suddenly equals 2, suddenly equals 1. I mean. And by the correct definition of the limit, it doesn't matter what the value equals at that point, it only matters what happens near that point. And that's because in the correct definition of the limit, we have this condition that says that x does not equal x naught in the definition. Okay. So let me just write out again the correct definition. Okay. So this first bit was correct. And for the last bit, oh, we need to put in this 0 less than the absolute value of x minus x0. And that makes sure that x is not equal to x0 in the definition. Okay. So after that, let's talk about a very useful idea, one-sided limits. And these are very helpful to allow us to better understand when a limit exists or not. Okay, so definition. Let fx now be defined on x0 to b. So you remember last time, I can still see there, we had an interval a to b where the function was defined. And x0 was somewhere inside that interval. So now the situation is slightly different. We have x0 and b, and we're asking that the function is just defined between them, but we're still going to take the limit at x0. Okay, so the domain of the function is that. Then limit of fx as x goes to x0 from the positive side, so you see I put in a plus there, if okay. So the definition goes like this: for all epsilon greater than 0 there exists delta greater than 0 such that if x is between x naught and x naught plus delta, then the value f of x is within epsilon of L. Okay, so again, I'm going to put that in a box. That's the important bit. Okay. And in this case, we say the right-hand limit of f, because the x's we consider are approaching x0 from the right on the number line. Okay. So the x's are between x0 and x0 plus delta. Okay, so of course there also exists an idea of left-hand limit. So let's write that out. We just swap everything around. Should I make this the same x0? Yes. So now we have a point to the left of the x0, which we call A, and we let the domain be the numbers between those two. And now we're going to take numbers approaching from the left side. So we're going to take x is between x0 minus delta and x0. Okay. So I'm going to write this second definition in blue. So I take fx to be defined on open interval a to x0. Then the limit the left-hand limit now, and I write this, x goes to x0 minus equals L if, well, the same thing, but I ask for x to be in the interval from the left, given like that. And so in just the same way, we say the left-hand limit. Okay. So this is useful, for example, at the edge of where a function is defined. So the right-hand limit of the square root of x as x goes to 0 is 0. Okay, so how to prove that? Well, for each epsilon, I just take delta equals epsilon squared. Okay. And this is useful because in this case, the limit does not exist. As x goes to 0, but the right-hand limit does. And that's just because the domain of the function is the positive real numbers. So domain is r plus. Okay. So note these conditions. So this condition on x is, of course, equivalent to our previous condition on x, this condition on the absolute value of x minus x delta, and x is greater than x0. So, i.e., x is on the right. Of x0. So another way to say it is the right-hand limit just considers the values of the function to the right of x0, where we want to take the limit. Okay. Now, just by considering these three definitions, the limit and the left and right limit, we get a theorem So the theorem the limit at fx exists and equals L at C if and only if the left-hand limit exists and the right-hand limit exists. Okay. So, in other words, limit exists if and only if left and right-hand limits exist. And they are equal. Okay, so for example, if I take ux, the unit step function, so this is 0 for negative x, and it is 1 for positive x and for 0. So ux, we said that lim ux, x goes to 0, does not exist. And y, well, the left-hand limit of ux is 0. So you can check that from the definitions, but it's just true because you're only considering negative values of x, and the function is always 0. So the limit can't be anything else. And the same applies to the right-hand limit. So that must be 1. So I meant, although what I'm saying is still correct, but I meant to let this function be defined at 0 and have value 1. Okay, so by the theorem, the limit of ux as x goes to 0 cannot exist. Okay. Right, but it's possible one limit can exist, but not the other. So let me try to find the graph of the sine 1 over x function that we considered last time. Here we are. Yeah. So this graph from last time. So in this case, the limit from the left-hand side of this fx is 0, but the limit from the right-hand side does not exist. Okay, so remember we proved last time that the limit doesn't exist because the function oscillates too much. So it's still true that because the function oscillates too much, there is no limit on the right, but on the left it doesn't oscillate at all. So there is a limit. From the left it equals 0, but the limit on the right does not exist. Okay. Okay, I'm checking questions. Yes, so a question from Zhang. That's correct. So the epsilons and deltas are for proving a limit claim. To calculate, to actually find the limit, you will use limit laws and sandwich theorem and things like this. So. But the proofs of those theorems use epsilons and deltas. So, okay. Okay, so another example. If I let gx is the square root of 4 minus x squared, so this is the equation of a circle. radius 2. So in this case, the limit of gx as x goes to 2 from the left is 0. And the limit as x goes to minus 2 from the right, gx is also 0. So even though the limit as x goes to minus 2 of gx does not exist, and why? Well, because the domain is equal to the interval minus 2 to 2. So the definition of limit does not apply. We need, for the limit, to have an open interval where the function is defined containing the point we're interested, minus 2 in this case. Okay, so theorems for one-sided limits. So limit laws sandwich and comparison theorems these still hold. Okay. So for example, if the limit of fx as x goes to x0 from the right is L, and the limit of gx as x goes to x0 from the right is M, then the limit of the sum equals the sum of the limits. But of course we have to continue to take the limit from the right. And so proof as in previous class. Okay, but this shows you, so for the limit laws, we have to replace x goes to x0 with x goes to x0 plus, or x goes to x0 minus. And for the sandwich and comparison theorems, we have to replace, so remember the domain was AB with C removed. Let me draw a picture here. Okay, so the domain was AB with C removed, ABC, like this, and we were taking the limit at C, But if we're still taking the limit at c, but from the left, yes, let's get this right. In that case, we take domain A to C, but if we're taking the limit from the right, we take domain C to B. So maybe I'll put in some arrows there to remind you. So we're taking the limit, curly arrow, taking the limit from the left, or we're taking the limit from the right. Okay. So let's do an example where one-sided limits are useful to calculate a full limit. So for calculation, so note if I know the limit of a function fx from the right, let's just say the limit of the right as fx goes to 0, then I know the limit of f minus x as x goes to 0 minus. Remember putting in minus x there just reflects the function. So exchanges left and right, and so this limit is also L. And we can reverse that process. So this is an if and only if. So example calculation. From last time, we did some spreadsheet calculations that showed that the limit of sine theta over theta as theta goes to 0 seemed to be 1. So now let's prove that. So call this f theta. So proof using a carefully chosen picture. How does it go? So we take a sector of a circle. Yeah. Get this angle right. Yeah, that will do. So we take a sector of a circle or a piece of pi, but the angle here is not pi, it's some theta, and that theta is going to be small later. And now I want to calculate sine theta over theta from this diagram. So actually I can't quite do that, but I can get close enough to calculate the limit. So let me show you how. Let's draw in two triangles like this, back out, and let's start defining lengths on this. So let's say this length, the radius of the circle, is 1. In that case, by the definition of sine, the height of this triangle is sine theta, and the height of this triangle, let me make that better. The height of this triangle is tan theta. Okay, and so I now want to calculate areas. That's the trick. Let me first calculate the area of this piece of pie. So this area is half theta r squared. So you can remember that if it was the whole of the pie, if theta equals 2 pi, then area is pi r squared. But in this case, we have a smaller slice of the pie, and so the area is half theta r squared. But of course, that's just half theta. And then comparing with the areas of the triangles, well, inside the slice of the pie, there's a triangle with height sine theta and base 1, so its area is half sine theta. So that's obviously less than the area of the slice of the pie, half theta. And it's also less than the big triangle, the one of base 1 and height tan theta. Okay. So now this implies, and I'm going to assume here that theta is not equal to 0, that if I divide through by sine theta, and I'm also going to ask for theta to be small, because otherwise, if theta is pi, it can be 0 again, so I couldn't do this. But I'm asking for theta to be small. And then I can do this, divide by sine theta. And I can also take 1 over things, because these things cannot be 0. But if I take 1 over, then I have to change the direction of these inequalities, as you will know. So I get that. And so we can use the sandwich theorem. So hence by sandwich theorem, the limit of as theta comes from the right of sine theta over theta is 1. And that's using, because as we know, the limit as theta comes to 0 from the right of cos theta is 1. Okay, great. Let's take a break. Thanks for the comments in the chat. Yes, that's correct. Okay, so I just drew a picture of the sandwich here. So the function sine theta over theta for positive theta is sandwiched between cos theta and 1. Okay, but in our construction, we wanted our angle theta to be positive. That's the picture we drew. But this function, but f theta is an even function. So the limit as theta goes to 0 from the right, sorry, as theta goes to 0 from the left, whatever that is, it must be the limit as theta goes to 0 from the right of f minus theta. And that is equal to the same limit of f theta, because this function is even. And we know that to be 1. So, by a theorem above, that if the limit from the left and the limit from the right exist and are the same, we get that the limit of f theta as theta goes to 0 is 1. So that completes the proof of the claim. Okay, so in this second half of the class, I'm going to talk about the second big topic in this section. We'll come back and do different sorts of limits later, but didn't want to do all those at the same time, so I want to get on to one of the most important things about limits. They allow us to define continuity of a function. And I'm going to give an informal definition of continuity. So say a function is continuous if its graph can be drawn in one continuous motion. Without lifting pen from paper. Okay, so this is not a very good definition of continuity because we saw that some functions you can't really draw at all. I mean, this function sine 1 over x, which is oscillating like this, you can't really draw it, but this gives you an idea, and it can show you clearly where certain functions are continuous or not. So let's take this example. So the function defined by this graph has domain the closed interval from 0 to 4. We can see that it's defined at 0, and it's also defined at 4. And you can also see by this informal explanation that we can draw the function by continuous motion up until 1, and then we can keep going from 1 up until 2, and then we can keep going up until 4. So it's true, we will prove that this is continuous except at points 1, 2, and 4. And so these x values. So we can see we couldn't draw it with one continuous motion of the pen, but note that mathematically we can make these observations. That at 1, the limit of fx does not exist. That's because the function jumps from 0 to 1. And as x approaches 2, the limit does exist. So remember, the limit doesn't depend on the value of the function at 2, it just depends on the values near the 2. And when x is near to 2, the value of the function is near to 1. So the limit equals 1, so it exists. But it's not equal to the value of the function, f2, because the value of the function is 2. Okay, and in the same way, the limit of fx as x goes to 4, from the left, I have to be careful to take from the left and that's because domain is 0 to 4. So the limit from the left equals 1. But it is not equal to the value of f at 4, because the value of f at 4 is less than 1, I guess it's a half. Okay, so how to define when a function is continuous? Well, let's first introduce some terms. So first, the left and right endpoints of the domain. Let those be 0 or 4. And let's talk about the interior of the domain. Is points x where x is strictly between 0 and 4. And then I'm going to define continuity at a point as follows, but in 3 different ways, depending on what sort of point we're talking about. So the first case is if I have an interior point, say C. Then I say that f is continuous at C if the limit of fx as x goes to C equals the value of the function fc. Point. And now I'm going to have 2 other definitions for left endpoints. And right endpoints. So if I have a left endpoint A, say f is continuous at A if the limit of fx as x goes to A from the right is fa. And the opposite thing for a right endpoint B that f is continuous at B if the limit of f of x as B as x goes to B from the left is FB. Okay, so drawing a picture. So the domain here could be from A to B, that, and I'm taking a point C in the interior of the domain. So note in particular, to be continuous at a point, in each case, a limit must exist. So at an interior point, the usual limit must exist. At one of the endpoints, a one-sided limit must exist. But in each case, a limit must exist. And a function must be defined at the point. Because the definition of continuity says that the value of the limit equals the value of the function. So of course the function has to be defined, the limit to exist. Okay, so question from Leah Chen. Did I make a mistake? Is that the last slide? Yes, correct. Thank you. equals 1. Thank you, Leah Chen. Okay, and terminology say that a function f is discontinuous at, I just spelled that wrong, is discontinuous at x0, say, if it is not continuous. X0. Okay, so example, if P is a polynomial, then the domain of that polynomial equals R. And we saw before that the limit as x goes to any c is just given by calculating the value of the polynomial. So P is continuous for all C in R, so for all points in its domain. Okay, so another example. If I take y is the square root of 4 minus x squared, so this was a semicircle. This is continuous for x in this interval. So that's the domain. And that's because at the endpoints, the left-hand and right-hand limit exists, and they're both 0. We saw that just before, and the value is also 0. Okay. So another example, ux. So remember, this ux was 1 for positive and 0 for negative. And its domain equals R. And it's continuous for points x in R with 0 removed. So why is it not continuous for x equals 0? because the limit of ux as x goes to 0 does not exist. So 0 is an interior point of the domain, so we need the function to be defined at that point. It is defined, it equals 1 and 0, but we also need the limit to exist. In this case, the limit does not exist. So just one more example. Now, if I take y is 1 over x squared, y equals 1 over x squared. So this is discontinuous. At 0. Because the function is not defined. 1 over 0. Okay, so we've talked about how a function can be continuous at a point or not. We also talk about a function being continuous. And this matches with our idea of you can draw the graph without lifting the pencil from the paper in continuous motion. So the definition, let's just give the function f is continuous on an interval just say it in words, if it is continuous at every point of that interval. Okay, so for example, we saw before y is the square root of 4 minus x squared on the interval -2 to 2. So it's not defined outside of that interval, but it is continuous on that interval. So it's also useful to say a function f is continuous. And sometimes we'll say continuous on its domain. If it is continuous, at every point of its domain. So, for example, y is Square root of 4 minus x squared. But also y is 1 over x. So in this case, domain minus 2 to 2. In this case, what is the domain? It is a union of two open intervals. Let's draw the graph to remember. So this is the graph of y equals 1 over x. The domain is everything except 0, the union of those two open intervals. And the graph is continuous on that domain. Okay, so how to prove things like this? We can use limit laws. And they become continuity laws, some useful theorems for checking continuity. So I'm not going to write them out as a theorem, but I'm just going to explain what is true. If functions f and g are continuous at x equals c, then these functions are also continuous. So if I add the functions together, if I subtract them, if I multiply them together, remember this means multiply. If I multiply a function k, if I multiply a function by k, for constant k r, then that function is also continuous at x equals c. Same is true for the quotient, f over g. And as you might expect, for this we require that the value of g is not 0. So this example here is a demonstration of that, that 1 over x, f over g, is continuous wherever g is not 0, i.e. wherever x is not 0. Okay, and now, just finally, f to the power r over s r over s that are s integers. Okay, and for this I also need some condition. Also require this to be defined on some interval AB containing. So let's call that star. I'll say you know why star is important, but I'm just coming back, see if there are any questions. So the Cantor function is a very interesting function, but it is beyond this course. Yeah, I'd be interested to have discussions about that after class. Thank you, Octavio Molina. No. So, how can we prove these claims that f plus g is continuous if both f and g are? Well, let's just prove the easiest one. Some other proofs are in the book. So for f plus g to be continuous, I want the limit of f plus g, a function of x, as x goes to c, to be equal to the value of that function at c. Now, by definition, the value of the function at x is the sum of the values of f and g at x. And the limit law says that the limit of the sum is the sum of the limits. But we know these two functions are continuous at c. And so say they have limits L and M, then those limits are going to be FC and GC. So actually we don't need this line. We can just say those limits by continuity of f and g. And this is the value of the function f plus g at c. So that proves that f plus g continues c, which is what we wanted to prove. Okay, so remark, we need this condition star because if fx equals x, and I take the limit with c equals 0, then 1 over x, so I guess I need to say what r and s is. And if r is minus 1 and s is 1, then 1 over x, so that's the function f to the power minus 1, 1 over x is not defined. On any interval AB containing 0. So the limit law doesn't work, so we can't say the function is continuous at that point, and indeed the function is not continuous. Okay, we'll give some more examples, and then talk about compositions of functions. And maybe we'll give an interesting example at the end. So composition of functions. So, for example, the function f then g. So this circle means composition. That means we take, I'm drawing 3 number lines here. So we take, say, a point C, map it to FC, and then map FC to G of FC. So F does this, and G does this. And the composition F then G does this. Okay, I haven't drawn that very well, but you get the idea. It's going to this dot. So theorem. F continuous, let's see. I'm just writing cont for continuous. And G continuous, and the image of C implies the composition is continuous. Let's see. Okay. So let's make an example of this. I'll give another example of a continuous function first. Okay, I'm actually going to change the order here because otherwise it's going to be a bit confusing. So this is composition of functions. I just want to use this function absolute value to make an example. So this function fx, for x greater than 0, f of x, of course, is equal to x. So it's continuous. For x less than 0, f of x is equal to minus x. So it's also continuous. And for x equals 0, the limit as x goes to 0 of f of x, we already said, equals 0, and that equals value of f at 0. So we get that the function f is continuous. So let's use that to prove an example from the book. If I take y is x minus 2 over x squared minus 2, then this function is continuous on its domain so it's defined, its natural domain is where x is not equal to the positive or negative square root of 2. So why is this? We use theorem with fx is x minus 2 over x squared minus 2, and ex is the absolute value. Because then y is the composition f then g applied to x. Okay, so 2 more minutes. I'll just finish with the idea of continuous extension. So this concludes our discussion of the function, where is it? Yes. Sine theta over theta. So here's a graph of the function sine theta over theta. So f theta has domain r with 0 removed, because we can't divide by theta equals 0. But can extend f to point 0 as a continuous function. And so how do we do that? Let's take capital F, f theta, to be sine theta over theta, just as before, for theta not equal to 0. And let's just choose the value 1 for theta equals 0. And this is continuous at, because its value equals little f0, and it's continuous at theta equals 0, because the limit as theta goes to 0 of f theta, well, that doesn't matter what the value theta is, it's just going to be 1, and that equals the value S0. Okay. Okay, thank you. So next class is Saturday. Next class is Saturday.